So the first question here asks us to consider the equation given here. First thing, we see an unbalanced equation, so that means that we're going to want to go ahead and balance it. So since I've got H and OH, right away I'm going to rewrite water as HOH. That way it's obvious that I have hydrogen and hydroxide on both sides of the equation. So right away we see there's two sodiums here. So I'm going to need to put a 2 in front of the sodium hydroxide. That gives me 2 sodiums. It also gives me 2 hydroxides. So then I'm going to want to come over here and put a 2 to get 2 hydroxides. That will give me 2 hydrogens, and I've got 2 hydrogens here, so that's already set. There's 1 sulfate and 1 sulfate, which means that in front of these other 2 blanks we just have 1s. The next question is asking for the limiting reactant if 20 grams of NaOH, which is our first given, react with 22.5 grams of H2SO4. So whenever you do a limiting reactant problem, your first step, ensure that your equation is balanced. Then you're going to want to pick a product. Now we want to choose wisely based on the problem. So if the problem asks about a specific product, we're going to choose that one. So this question doesn't ask about a specific product, but if you read down in B and C and you look down, all of those questions are asking about sodium sulfate. So we're going to go ahead and pick sodium sulfate as our product. You could have easily picked the water and figured out the limiting reactant as well, but since the next questions are asking about sodium sulfate, we might as well pick that one. Next, we want to determine how much of our product we can make with each of the given amount of reactants. So this usually means 2 calculations. So we're going to use our 20 grams of NaOH and see how much sodium sulfate we can get, and then 22.5 grams of H2SO4 in a separate calculation, see how much sodium sulfate we can get. Now, the units for how much depend on the problem. So if we're just asking for limiting reactant, we can just do moles. But if the problem, or one of the following problem, asks for grams or liters or particles, then we should choose that as the units we solve for. And then whichever one makes less is my limiting reactant. Now this problem asks for Na2SO4 in grams, and down here it asks you to find molarity. So I'm going to solve both of these for moles of Na2SO4, and then here I'll just convert it to grams, and then here I'll use the moles to get molarity. So let's do our pink calculation, the 20 grams of NaOH first. So I'm going to start with 20.0 grams of NaOH. Our first step, whenever we do stoichiometry, is to take whatever we are given, in this case, grams of NaOH, and convert it into moles. So our first step is to take whatever we are given, change it into moles. Once we're into moles, then we can do a mole ratio. So I'm going to do the mole ratio of NaOH to the mole ratio of Na2SO4. And again, I only picked Na2SO4 because the problems later on ask about it, so I might as well calculate it. So this first one here is grams and moles. So we're going to need to find the molar mass of NaOH. So to do that, we've got 1 sodium, 1 oxygen, and 1 hydroxide. We look up these molar masses on the periodic table and then total them up. So I get that 1 mole weighs 39.997 grams. Molar mass is always the mass of 1 mole of a compound. Next, we have moles and moles, so that means that we have a mole ratio. So mole ratio comes from the balanced equation. In the balanced equation, there is 1 mole of sodium sulfate for every 2 moles of sodium hydroxide. So whenever we solve, I get a 1/4 mole of Na2SO4. So I rounded this for sig figs because this has 3 sig figs, so this should have 3 sig figs. Now we're going to go ahead and tackle the green calculation, which is the 22.5 grams of H2SO4. So I'm going to start with 22.5 grams of H2SO4. Just like last time, my first step is to take whatever I am given. So I'm given grams of H2SO4, and we want to change this into moles of H2SO4. Once we're in moles, we can do a mole ratio. So moles of H2SO4 on bottom and moles of Na2SO4. You want to make sure that you get both answers in the same units. That way you can compare them. So my first blank here is grams and moles, which means molar mass. So for H2SO4, there's 2 hydrogens, so I have to double the molar mass of hydrogen, and 4 oxygens, so I have to multiply that by 4, and then add it all up. So I get that 1 mole of H2SO4 weighs 98.078 grams. Next, we have a mole ratio. So that comes from the balanced chemical equation, and that ratio is 1:1. So when I solve this, I get a little bit less than what we got before. And again, I'm using 3 sig figs here. So between these two, whichever one makes less of our product that we've chosen, that one is going to be the limiting reactant. So that's going to be the 25 grams of Na2 of H2SO4. That's my limiting reactant. So the next question says, okay, well then what is the theoretical yield of the Na2SO4 in grams? So the most Na2SO4 that we can make is 0.229 moles. I can't make 0.25 moles because I'm going to run out of this H2SO4 first. So I just want to take the moles of Na2SO4 and just convert it to grams because that's what this problem asks for. So I'm going to convert moles of Na2SO4 into grams of Na2SO4. So to do that, once again, I need the molar mass. This time I need the molar mass of sodium sulfate. So that's 2 sodiums, 1 sulfur, 4 oxygens. So I have to double and multiply by 4 here. And when I total it all up, I get that 1 mole weighs 142.042 grams. So now I just need to solve here, and I get 32.6 grams of sodium sulfate, and that is again with 3 sig figs. Okay, the next question says, assuming that the total volume is 0.25 liters, what is the molarity of the Na2SO4? So molarity is moles over liters. So we know the moles of Na2SO4. That's what I got up here. So I can form this many moles of Na2SO4. And it says that the volume is 0.25 liters. So I just need to divide these two. And with 2 sig figs, my answer is 0.92 molar. Next question says, why is it important to know the limiting reactant in a reaction? And that's because the limiting reactant is going to tell us how much product we can make. So the amount of product that we can make depends on the limiting reactant. And sometimes if we're doing a reaction, we might be aiming for a certain yield. And limiting reactant is going to dictate how much of that product we can make. Last question on this page says that the student does the reaction and they get 29.60 grams of Na2SO4. So this is their experimental yield. This is how much they got when they actually did the experiment. So to find the percent yield, we need to take the experimental value divided by the theoretical value times 100%. So my experimental value is the 29.60 grams, and the theoretical value is what we figured out in question B up here. So I'm going to put that on bottom. So whenever I do this math here, my answer is going to need to have 3 sig figs. So I get 90.8 as the percent yield. So the next question, again, we have an unbalanced equation, so I need to balance this before I get started. So we've got 1 potassium here and 2 potassiums here, 1 hydroxide and 2 hydroxides. So I'm going to put a 2 in front of that, so that takes care of the potassium and the hydroxide. 1 copper here, 1 copper here, 1 sulfate here, 1 sulfate here, which means the rest of these just have 1s in front of them. So the first question says, how many moles of KOH do I need to prepare 12 moles of K2SO4? So we're going to start with our 12 moles of K2SO4, and this just wants moles of KOH, so we can go straight to a mole ratio. So mole of K2SO4 on bottom and mole of KOH up top. So this is just a mole ratio. There's 2 moles of KOH for every 1 mole of K2SO4. So my answer here is 24 moles of KOH. The next question asks for moles of copper sulfate, and you are given, this time, 4 moles of KOH. So this is just going to be another mole-mole conversion. We've got 4 moles of KOH over 1, and we want to convert moles of KOH into moles of CuSO4. So this is just another mole ratio. It's 1 to 2. So this gives us 2 moles of CuSO4. Number 3 says a solution is made with 150 grams of sodium chloride in 800 milliliters of water. What is the molarity? So molarity is equal to moles over liters. So if we can get the moles of NaCl and the liters of water, we can get the molarity. So I'm going to start with my 150 grams of NaCl, and I just want to convert grams into moles. So this is just a conversion. So grams of NaCl on bottom and moles of NaCl on top. So this requires the molar mass of sodium chloride. So there's 1 sodium, 1 chloride, so the total molar mass is 58.443 grams per mole. So 1 mole weighs 58.443 grams. So whenever I solve this, I get 2.567 moles of NaCl. So now we have the top, we just need to get the bottom. So for the bottom, I'm going to take that 800 milliliters, and I just want to convert milliliter into liter. So 1 liter is 1,000 milliliters, so this gives me 0.8 liters. So now to get my molarity, I just need to divide these 2 numbers. So I'm going to do 2.567 moles divided by 0.8 liters. So my answer here, I get 3.2 molar as my concentration. Number 4 is asking a little bit different of a question. It's asking for moles of HCl if you have 10 milliliters of 6 molar HCl. So once again, molarity is moles over liters. So if we know the molarity and the liters, we can solve for moles. So I do know the molarity, it's 6 molar. I'm solving for moles. I need the liters. So here I have 10 milliliters. I'm just going to convert a milliliter into liter. So 1 liter is 1,000 milliliters. So that gives me 0.01 liters. So I'm going to put that on bottom here. So to solve for x, I need to multiply both sides by the denominator. So whenever I do that, I get 0.06 moles of HCl. At this point, we could use this number to do stoichiometry or to do other problems with it, but we know the moles of HCl. The last question, number 5, says look at this reaction and determine what metal X could be such that the reaction occurs and such that the reaction does not occur. So this is going to require our activity series. This is a single replacement reaction. So X is going to replace magnesium if and only if it's more reactive than magnesium. So find magnesium on our activity series. So if I want a reaction that will occur, I can do any of the metals above magnesium. So I'm just going to do sodium and calcium. Those will work. For a reaction that does not work, I need to pick something that is below magnesium. So any of these things below will work. So I'm going to pick aluminum and manganese. So question 6 has a bunch of equations for us to write and balance. So let's get started with the first one. So potassium metal and chlorine gas combine to form potassium chloride solid. Okay, so potassium metal, that's just going to be K for potassium, and it's a solid. We don't need to worry about charges or anything because it's just a pure element. There's no charges to worry about. And then we have chlorine gas. So chlorine is Cl, but chlorine is one of the 7 diatomic elements. So those 7 diatomic elements, you can remember them with have no fear of ice cold beer. So all of these, when you encounter them by themselves, are diatomic. So if we encounter chlorine gas, that's chlorine by itself as a pure element, this is going to be Cl2, and it's a gas. So this applies when we have a pure element. Okay, so now that we've got our chlorine gas, our product here is potassium chloride solid. So potassium is a metal and chloride is a nonmetal, so this is an ionic compound, which means that I need to worry about charges. So the charge on potassium is +1 and chloride is -1, so those charges work out to be neutral, and we just need to put an S for solid. Now this one's real easy to balance. We've got 2 chlorines here and only 1 here. So I'm going to put a 2 in front of the KCl. That gives me 2 chlorines, but it also gives me 2 potassiums. So I'm going to put a 2 here. So this is a synthesis reaction because 2 things come together. This is also sometimes called combination because 2 reactants combine to give us 1 product. The next question is solid copper reacting with sulfuric acid, and we're going to get aqueous copper 2 sulfate, liquid water, and sulfur dioxide gas. So solid copper, that's just copper metal, pure element, so we don't need to worry about charges. So just solid copper. And that's going to react with sulfuric acid. So whenever we name acids, the name and the ending of the anion depend on each other. So I have sulfuric acid, I have blank-ic acid, which means that this sulfur originally ended with 8. So I originally had, for my anion, I had sulfate. So sulfate is SO4 with a -2 charge. This is an acid. Acids start with hydrogen, and the charge on that is +1. So I need 2 hydrogens to balance out the charges. And it tells us that it is aqueous. Okay, got a lot of products here. First I have copper 2 sulfate. So that Roman numeral 2 is telling me the charge on copper is +2. Sulfate is SO4 with a -2 charge. We already have that over here. So those charges work, and it says that this is aqueous. We're also going to get water, which is a liquid, and sulfur dioxide gas. So for water and sulfur dioxide, these are covalent compounds. They're both nonmetals, so I don't need to worry about charges. Water is just H2O, and sulfur dioxide, there's nothing in front of the sulfur, so that means 1, and di means 2 oxygens. So this one's a little trickier to balance, so I'm going to go ahead and take inventory. We do have sulfate on both sides, but we also have some oxygen and sulfur over here too. So I'm just going to list each element individually to balance this one. So I've got 1 copper, 2 hydrogens, 1 sulfur, and 4 oxygens. And then on this side, 1 copper, 2 hydrogens, and I've got sulfur in 2 places, so that's 2 atoms of sulfur. And then oxygen is in 3 places, so there's 4 here, 1 here, and 2 here, for a total of 7. So that's kind of ugly, especially this 4 and this 7. So what I like to do whenever I encounter this even-odd situation is say, what can I do that will make this an even number? So if I do anything to this, that won't help me. Anything to that won't help me. The odd comes from this 1 oxygen. So if I put a 2 in front of this, that'll give me 8 oxygens total and 4 hydrogens. So if we look, we got 2 and 4, 1 and 2, 4 and 8. So if I just double this H2SO4, that'll give me 4 hydrogens, 2 sulfurs, 8 oxygens, and now we're balanced. So this is a single replacement reaction, and we know that because the copper is replacing the hydrogen. So instead of H2SO4, we have CuSO4. The next equation to balance, so we're going to have sodium phosphate reacting with calcium chloride solution. We form sodium chloride solution and calcium phosphate precipitate. So sodium is a metal and phosphate is a polyatomic ion. So I know right away that I need to worry about charges. So sodium is +1. Phosphate is a polyatomic ion with a -3 charge. So I'm going to need 3 sodiums to balance out these charges. And it tells us that this is a solution. That reacts with calcium chloride, so I got a metal and a non-metal. Need 2 chlorides to worry about our charges to balance that out. It says that it's a solution. And we're going to make sodium chloride. So once again, I have a metal and a non-metal. This time the charges work out, and this is a solution. And we get calcium phosphate. So if I crisscross my charges here, I need 3 calciums and 2 phosphates, and that one is the precipitate, so that's a solid. So to balance this one, I'm going to take inventory. I've got sodium, phosphate appears on both sides, calcium appears on both sides, and chlorine on both sides. So I've got 3, 1, 1, 2. And over here, I've got 1, 2, 3 calciums, and 1 chloride. So I'm going to go ahead and fix the calcium first. So I'm going to put a 3 here. That gives me 3 calcium and 6 chloride. And I'm going to go ahead and fix the phosphate now. so I'll put a 2 here. So that gives me 2 phosphate, but it also gives me 6 sodium. So I've got 6 sodiums and 6 chlorides, so I want to put a 6 on this side to get 6 and 6. And this is a double replacement reaction. And we know this because the sodium and the calcium are switching spots. So number 7 asks us to predict the products and write out net ionic equations. So these are all double replacement reactions. So I'm going to need to switch my sodium and potassium or calcium cations. So I'm going to figure out the charges. Sodium is +1, nitrate, polyatomic ion, is -1, calcium +2 from the table of elements, and hydroxide is -1 from our polyatomic ion sheet. So I'm going to swap the sodium with the calcium, just switch spots. So I'm going to get calcium nitrate. So to make these charges neutral, I need 2 nitrates. And I'm also going to get sodium and hydroxide, and those charges already work out. So to figure out if this reaction happens or not, we're going to need to consult our solubility guidelines. So this is a nitrate compound. Nitrate compounds are always soluble, no exceptions, so that means it will be aqueous. This is sodium hydroxide. Sodium is a group 1 ion, which are always soluble, so this one is aqueous as well. So we're not going to bother writing out a net ionic equation because we can't, because nothing happens. There's no reaction. Going to apply the same procedure for B. So identify charges on everything. Lithium is +1, hydroxide is a polyatomic ion with -1 charge. I don't know the charge of copper from its position because it's a transition metal, but I do know the charge on sulfate is -2. And there's only 1 copper, so the charge on that 1 copper must be +2. So I'm going to switch lithium and copper. So I'm going to get lithium sulfate +1 and -2, so I need 2 lithiums. And I'm also going to get copper hydroxide. So I'm going to need 2 hydroxides to balance out the charges. And once again, we're going to consult our solubility guidelines. Lithium is a group 1 ion, which is always soluble with no exceptions. Hydroxide is usually insoluble unless we have group 1 calcium, barium, strontium, or ammonium. Don't have any of those here. So lithium sulfate, aqueous, calcium hydroxide, solid. So for this one, we can write our net ionic equation. We started out with hydroxide -1 aqueous and copper +2 aqueous, and those came together to give me a solid product. So I don't care about the lithium because it starts aqueous and ends aqueous. I don't care about sulfate because it starts aqueous and ends aqueous. So I don't care about either of those. I only care about my product that is not aqueous. Real quick, we can see that this isn't balanced. There's 1 copper, 2 hydroxides, 1 hydroxide. So I'm going to stick a 2 in front of the hydroxide ion. For question 8, this is similar to chemistry, where we have 4 unknown bottles, and we have to identify which one is which. So the possibilities are lead nitrate, hydrochloric acid, sodium carbonate, and barium nitrate. So first and foremost, I want to point out A gives me 2 solids, B gives me a solid and also forms bubbles, C is 2 solids and bubbles, and D is just 1 solid. So these all react very differently. So all I need to do here is just match the number of solids and bubbles based on all of the possible reactions. So I went ahead and wrote out the reactions. So these are my lead reactions, the HCl reactions, the sodium carbonate reactions, and the barium nitrate reactions. So all I did here was react each thing with all of the other things. So we can go ahead and start predicting some products here. Obviously, lead nitrate isn't going to react with itself, so we know that's no reaction. This bottom one, even if lead and barium switch spots, we don't get anything new. We still get lead nitrate and barium nitrate. So that one is also no reaction. Now for these two in the middle, we don't care about nitrate because we know that any nitrate compound is going to be soluble. So what really matters here is the lead. So whenever we switch cations, we'll switch lead and hydrogen. I'm going to get HNO3. Again, don't care about that because it's nitrate. We know it's soluble. But I'm also going to get lead chloride. So we need to check our solubility guidelines. Lead compounds are pretty much always going to give us a solid. Here, we're going to get sodium nitrate. Don't care about that because nitrate is always soluble. And lead carbonate. If we check our solubility guidelines, that is also a solid. So right away, I can identify one of my four things here, because the thing that gets two solids, like what we see for lead, that has to be lead. So A, we've identified already as the lead nitrate. Okay, let's take a look at the sodium carbonate reactions. So if these guys switch spots, we've already done this reaction over here. So we're going to get PbCO3 solid. We've already accomplished that one. Whenever these guys react, we're going to get NaCl, but we're also going to get hydrogen carbonate. So we're going to get H2CO3, which will decompose into bubbles. So that's our bubbles right there. This one, obviously, not going to work because we're mixing it with itself. And this one, if we switch spots here, we're going to get sodium nitrate. Don't care about that because nitrates are always soluble. But then we get barium carbonate. So if I look at my solubility guidelines, carbonates are usually soluble, or usually insoluble, unless combined with group 1 or ammonium. That's not group 1 or ammonium, so there's a solid. So this gives me two solids and bubbles, so I can identify that. So two solids and bubbles, that's C. So that's going to be our sodium carbonate. So that just leaves my HCl and my barium. Now by the process of elimination, I'm not going to need to do both of these. I only need to do one because I only have two possibilities left. So the HCl and the lead nitrate, we already did that one up here. So that gave us a solid. This one is obviously going to be no reaction because it's reacting with itself. And this is going to give us bubbles. We already did this one over here. So this will give us bubbles. And then here we're going to get, switch these two, we're going to get hydrogen and nitrate. Don't care about that because nitrates are always soluble. But we will get barium and chloride. And according to my solubility rules, halides, like chloride, are always soluble unless combined with silver, lead, or mercury. That's none of those. So this one is going to be aqueous, which means no reaction. So the compound that has a solid and bubbles is going to be my HCl. So solid and bubbles, that's B, which means by elimination, that D must be the barium nitrate.